All right, we'll see if that works. All right, so I want to jump back to your electrical handout. We got started on this last week. We're talking about some other things. There's a couple things I want to cover today. A little bit of this handout, though. We covered power source pretty well, right? We said that we were looking at plus or minus 10% for single phase voltage. We laid out what we meant by single phase voltage, which also meant two power legs. We said for working on three phase, it was plus 10%, minus 5%, right? So a bit of difference there. Now what happens when you're working on control voltage, 24, that is still considered single phase. And so you go back to the plus or minus 10%. The next thing this thing looks at is conductors. And so we're looking at three things here. For the most part, copper wires and their connections, aluminum wires and their connections, and switches. Now, when I say switches, this can be a manual switch. This can be a switch with a flag, like a switch that opens or closes based on temperature or pressure or flow. Or it could be an automatic switch controlled by, say, a magnet, electric magnet or something, or a heat load like a sequencer. They're all considered conductors. Okay, so when anything opens and closes, there's a potential that we're going to get a spark or a gap as it closes or as it opens. So we always want to keep our eyes out to check for any kind of carbonization of the contacts. We're going to need a good closed contact, one that won't chatter, okay? And conductors need to be of sufficient size to handle the heat and the amperage. This is some of the most difficult troubleshooting is when you get loose conductors. I know back before I taught up here, I did a church. We put two heat pumps upstairs, but we put a split unit gas furnace downstairs with an AC sitting outside, and it was in the summertime. Everything was going good, and they called me about a year later, and wouldn't do anything. I checked it, had a 24 volt fuse, car fuse, and it was blown. So I either had two possibilities with the conductor. Either the unit had pulled more amps than the 5 amp or 3 amp, whatever it had in there, or it had a dead short, and that's why it pulled so many amps. And so what I typically do is I cut the power and ohm out that 24 volt circuit. Remember, this is all we're doing with this is typically breaking one hot wire. And on a 24 volt system, we only have one hot wire running through here. But if this 24 volt hot ever connects with 24 volt common ground, there's no load in it, and it's going to blow. And so usually the best thing to do is to ohm it out. Well, I had a measure of resistance. So we fought with that thing for a year or so. It would do fine for months at a time. Finally, one time when I got there, I ohmed it out and I had zero. I had a dead short still there. So I carefully went through every path that the transformer made. In other words, sending power to the R and the R sending it to the different things. Finally tracked it down to the Y terminal. We tracked to Y at the thermostat, and then it went ground. Went outside to the condenser, to the AC condenser, and right where the 24 volt thermostat wire went through the outside of the unit, the little rubber grommet had come loose. And when it would sit there and run, the compressor would have a little vibration, and it cut through the plastic conduit, and it cut through to the red wire, the yellow wire, I guess, and would ground. But when it kicked on and off, it wouldn't stay grounded. It would bounce around. So these could be very hard to find, okay? A couple questions you probably want to ask yourself is, was this run, has this ever run? You know, is this a brand new installation? You know, so that helps you, like, you'll have a tendency to say, this is messed up. And want to rewire it, you go like, this worked, you know, this worked at some point. Unless a technician or a homeowner got in there and rewired something, we just need to find the problem with it, okay? 26.2, disconnect switch open. All right, so what they're saying here is we're not getting any power across the disconnect switch, right? Now, we talked about the terminology with disconnect switch, right? The power flowing into the disconnect switch, we would call that the line voltage. And we would designate that with L1, L2, L3 if we needed, L4. And then across from it, the load side would be the T instead. And if it's the contact across from L1, so it'd be T1. If it was across from L2, then it would be T2, right? Yeah. Now, some of these disconnect switches are simply pull-out switches. That's all the code says, that we have the ability to cut the power without having to run inside to do it, the inconvenience. But that doesn't mean it's going to be that. They can sell you a disconnect that's fused. They can sell one that's breaker. They can have one with an arm out here. All kinds of them. But this disconnect switch is supposed to provide a means to cut the power off. So there's neither a right or wrong. So when you approach the disconnect, checking the voltage, you can check the line side or the load side, right? As long as you know what to do with that information. Let's say you're the kind of person that always checks the line voltage first. And you check, now what are the two ways to use our voltmeter? Across the source and across the load. There is no load here, right? Think about it. Load consumes power and does useful work. Well, this is useful. It cuts it on and off, but it doesn't consume power. And if it does, we got a problem. So, the only way our voltmeter will accurately tell us what it's got is across, right? Across the source. I have a leg coming in one side, leg coming in the other. Now, some of them are marked, some of them not. It's not like it won't work. All right, mine say, the two in the middle here, I don't know if y'all can see it, say line. So you'd have two powers coming in, two hot on the middle. And so the first thing you would test is across from L1 to L2, across the lines. Let's say you read the proper voltage. What would your next step be? The load side, that's right. And now, this load won't read without this in there, right? Trust me, these are made to disconnect it, which, you know, typically we recommend, twice a year to get it serviced. A lot of people don't do that once a year. These don't go in and out a lot. In here, with y'all working on them, they do. So it may be hard to get it in there right. Now, y'all going to have to eyeball it. You see how the copper line is lower right now? If I flipped it over, it's higher. And they printed on here, with it flipped over, it says OFF for off. In the right position, it says ON, on. But sometimes, you know, out there, you might not can read anything. So you definitely want to look in here and see where the actual contacts are in that groove. So you would need to close the disconnect, right? Which may make it harder to get your leads up in there to test the load side, right? But if this disconnect was working correctly and you had the proper voltage at the line side, what would you expect to see on the load side? Proper voltage. Now, what if you had gone directly to the load side with the switching in and you read proper voltage? What would be your next move? Move on down the line. I guess the contactor or whatever. But now, if you went to the load side and you had incorrect voltage, you would need to go back to the line side, right? And if you went to the line side first and you had improper voltage, there's no reason to go to the load, right? We just got to know when to go backwards and when to go forwards, okay? Inevitably, somebody is going to go across one side, right? That is not the way your meter works. Now, let's talk about what those possibilities. Let's say there is voltage there, and you're reading across an open switch. You may read voltage. Let's say there's voltage there, and you have the disconnect in. You're not going to read voltage. What if there wasn't voltage there to begin with? You're not going to read voltage. So don't confuse yourself with that, right? However, we said you could read across the source, so you can always read from one hot leg to a ground, because that's across a source to the ground, right? We could have 500 volts on each one. We could test them to ground, but make sure the ground is ground. Sometimes these things are not. Sometimes people make the mistake of putting neutral in there. These things aren't made for neutrals. But anyway, y'all feel pretty confident about testing a disconnect and the terminology. A lot of people call me up. Clay, I need some help. I'm going, what's my voltage at my line disconnect? I don't know. Well, it's going to be hard to help you. We don't know where we're at. You're not giving me good information, and I can't give you good information.
So on that breaker box, you said check the L1, both of the hots first.
Neither right is wrong, as long as you know which direction to go. If you read the first one and you got voltage, you move on toward the unit. If you don't, you got to move backwards. And this is a disconnect box because it doesn't have a breaker. You may have a disconnect that does have a breaker in it. Okay, now let's say you run across this disconnect switch. It does have proper voltage on the line, but it doesn't have proper disconnect of voltage at the load. Then we got a problem with the disconnect switch, right? For some reason, the power's not reading across it. What we're going to do then is we're going to cut our power, because what's our rule for using the ohm meter? That's right. No power and isolate, right? So let's read what they tell us to do here. On page 299 of our handout, last paragraph. If voltage is found across the line terminals and no voltage on the load side, it can be assured that the contacts are not closing. This can be confirmed by measuring the resistance of the closed contacts with an ohm meter, with the branch circuit fuses removed, circuit breakers open. We don't want any power. Now, measure the resistance of each set of contacts, in this case L1 T1, L2 T2, because that's all we've got. Now what does it say here? It says, any resistance reading over 1 ohm for high voltage, and they're saying for high voltage it's 50 volts or higher, defining it, or a half ohm for a low voltage, indicate burned contact and require replacement. So on our disconnects, on our breaker disconnects, on our fuse disconnects, or just our pull disconnects, if we get an ohm reading over 1 ohm, we got a problem, right? sometimes you can look at them and they're just all carboned up and black and charred. You know, and maybe you can sand them. You know, I always carry electrical contact cleaner, you know, for my contactor. But sometimes you can clean it up and work with it. But y'all, anytime we have a resistance reading, they're saying 1 ohm. That means not all the electricity is passing through here. We're creating at least heat. And as I create more heat, this thing's going to become a possible fire damage and melting damage. The last thing you want to do is reach in and pull it out and get yourself electrocuted, right? Okay. Main overload trip. Okay, we're going to come back to this, y'all. This is, look at the picture right under there, figure 26.5 here. So here we have, what we're talking about is basically a magnetic starter, or it's what we call a more complex contact or contactor. This is a contactor with some safeties, and these safeties have overloads in them. It's something we don't find in residential, but we do find in commercial a good bit. So we'll come back to that, okay? But right now I don't want to hit that. Blown fuse, I hit on the other day, right? It said right in the middle paragraph, 0.1 ohm indicates a burned fuse. Everybody see that highlighted? Did you need another one of these?
I got one.
Okay, all right. Okay. I think I want to stop right there on this. Okay. Now I want to talk about sequence of operation of air conditioning. Many of you are already aware of this, but as we begin to troubleshoot a system, you got to know the sequence of operation, or you're going to, kind of doing it with your hands behind your back. So the first would be sequence of operation. Now, it doesn't matter if we have a split unit or a package unit. So I'll just specify, first of all, I have to have line voltage. Now, if I've got a split unit, that means I have 2 units. That means I need line voltage at both units, right? If I have a package unit, that means I need line voltage at the package unit. Okay? Right. 2, I have to have control voltage. Now, as we get better and better troubleshooting, we're going to find that, our meter's not the only thing that helps. If I walk into a unit that's got a split unit, and I cut the thermostat, the fan on, and I hear the fan come on, the blower motor, well, I know the inside has line voltage because the blower motor's running. And the blower motor wouldn't have come on without control voltage, right? Now, there's always some options. Well, that doesn't mean I got line voltage outside, right? And that doesn't mean if I came in, if the blower motor's running, doesn't mean necessarily the thermostat's working or anything like that. It could be a ring. A lot of these rings, their default is when there's a problem with the board, they run the blower motor. So you go, the blower motor runs all the time. All right. Now, when we have this, we're going to have what we call a call for cooling in this case. We're not worried about heat, right? Now, many a poor technician has taken the word of a homeowner. The calls are cool, yeah. Go outside and start tearing the unit out, figure out what's wrong. They didn't put it in the proper setting. That means, depending on that thermostat, it's in the cool mode, and the temperature setting is low enough to bring it on, right? Well, I put it in cool, but you left it at 90. You know what I mean? Something like that. You know, a lot of times it's best that you go, well, I'm going to start with a thermostat. Not that they don't know what they're doing, but sometimes there's a communication gap. Like, he thought it was in cool because she said she put it on there, and she thought he put it on there. They're not trying to mess you up, they just did. Right? Okay, so, but this has to be satisfied. Alright? So now we start talking about what's going to happen next. What would happen next? We're going to expect the contactor to close. Now, what might keep that contactor from closing? A lot of things. Or maybe there's a pressure switch. This is a wire that runs outside, and that's a safety, right? Maybe it leaked all through. So we could have a pressure set, some kind of safety control open. The contactor mechanically may not can close. Somebody could have weed-eated the wire. But, I mean, there's a lot of reasons. But now, once we get here, if it doesn't, we've got to look for reasons why it didn't. Now, on a contactor, what we're looking here is it won't close unless I have 24-volt control, right? So if you look at it, it's not closed, probably the first thing you want to do is, do I have 24-volt voltage at the coil? And if you don't, why not, right? You're going to start looking at, is there a pressure stat open? Is there a wire loose? But if you do, the contactor should have closed, right? Maybe the contactor did, but you didn't have line voltage out there. That's another one of our, see, we went by. Or maybe the contactor itself is bad. It's got line voltage, it's got 24 voltage, but it's mechanically bad, either in the contact or the coil. Is that air or water?
I don't know what it is. Ain't nobody in there. That generator?
Might have been next door or something.
Ain't nobody in there.
Hello? I think they're working on the,
In the hall right there.
yeah,
The unit.
what, all right, let's say the contact closes, just like it should. What's going to happen now?
Let's go on.
Compressor, come on.
Keep going. Blower.
We're going to get
I mean, not blower, the
That's right.
fan, blower fan.
condenser fan, compressor, and blower motor should run. Now, let's talk about this. The thermostat, and I shouldn't say the thermostat, the majority of thermostats are set up when you put the thermostat in cool and you run the temperature low enough to bring on the cooling, in other words, it's calling, a a circuit is made to the blower motor relay. Right? Basically, a relay and a contactor are pretty much the same thing, except for we're dividing it by amps. Usually anything under 20 would be considered a relay. Anything over 20 amps would be a contact, although most of the relays we have use normally open and normally closed contacts, whereas the contacts we use are almost all normally open. So there's a circuit made when we do the calling, and all three should run, right? So if the blower motor doesn't come on, we could have a problem with the blower motor itself or the relay, right? Yes, sir.
When we got coming out to the contactor, that's coming from the thermostat. So we're not sending 110 out to the contactor. We're sending 24 from the thermostat to the contactor.
That's exactly
So
right.
I put my meter on the contact on the line side. I should get 24.
No. The line side, the contactor side also has a disconnect providing it with line voltage.
Oh, okay, so that's,
Two circuits.
okay, that's what I was trying to say.
Yeah, it has its own, unless it's a package unit, it has a 240 or 230 volt circuit out there, just like the inside.
Okay, so I'm gonna get 115 on the line. So coming out, then, you'll get on the low side. I'm expecting 24 volts.
No.
Still,
No.
that's why I'm confused with the call.
We call that control.
Okay.
We're going to use that voltage to control everything. It's going to control the line voltage, whatever that line voltage will be. That line voltage would be 230 inside unless it's a gas furnace, then we only need 120. Okay? So, now, I might add that the blower motor could also be a problem with a run capacitor. Okay? Everybody familiar with run capacitors? Okay. Couldn't be a start capacitor. We're not going to have a start capacitor on a blower motor. Okay? Now let's look at the condenser fan. The condenser fan could be bad. A wire could be burnt to it. Or its run capacitor could be bad. Okay? Now, the compressor. The compressor could be bad. The wires to it could be bad. The connection to it. The run capacitor. But on it, we could also see a start capacitor could be bad if it has one. And if we have a start capacitor, we're going to have a potential relay. Okay? And so the potential relay could either have bad wiring or it could be bad. Okay? So that pretty much sums up our sequence of operation. Now, you know, not everybody, but most people have had Brian's gas heat, right? He goes, and the sequence of that is a lot more complicated on now maybe not a basic pilot standing furnace, but on the new ones, trust me, it is. You got pressure switches and everything. So I want to go over that. Now I want to highlight how to use this Simu Air troubleshooter. So I'm going to go ahead and assign 10 for the semester. Okay? So on this computer, you look on the laptop, I got Simu pump, Simu refrigerant, Simu gas, and I'm looking for Simu Air. It looks like a little condensing unit. They're on up and downstairs.
Is that SIM?
Sim, S-I-M-U.
Oh, SIM.
Maybe there's a U on it.
Simu what?
Yeah, there's a U. This one's Simu Air.
AR.
A-I-R. So I'm going to click on it, or I should say double click on it. Give it a minute. I hope it works. I don't know why it wouldn't. So the first thing could have just made this thing bigger. Well, that mouse is not very. Oh, darn it. Anyway, I'm sorry, y'all. I was trying to make it bigger. You see up here, I don't know if y'all can read it, it says file. And down here, if you could see it, it says current user none. So the first thing you want to look is make sure the current user, because people are bad about not logging off, and you sit there and work for 30 minutes and you just stack their resume. So you want to hit file, you want user logon, and for most of you it's going to be new. These are not networked, and so every computer that you go to, if it's a different one, if you set next door than last time, you're going to have to log on to it, okay? They're not connected. And the programs, if you go from air to pump, refrigerant to gas, they're not networked. So you always got to log on. If you're new, just put new, type in some name. You do not have to have a password, y'all. There's nothing for anybody to steal. If you want to put it on, fine, but please remember it. I have no way of knowing what your password is.
You had this problem before, too?
Yes, I have. So I'm going to hit OK, and it's going to, no problem. If you've been on it before, you just get back on yours. If not, create another one. But the way I recommend it is at the end of the semester, I have to go to every computer with my roll sheet and see how many you've completed. And so I only do it once at the very end of the semester. The only way I can do it is if you use a name similar to the roll sheet, okay? So you can use any name you want, but you're not really going to get credit unless you use the roll name, okay? So now my name would show, or your name would show. So the first thing I'm going to show you is this program running normally without any faults. So I'm going to come over here and I'm going to hit run normal. So there's our system. I don't know if this will show it, but nothing's moving. And so to get it running down here, I've got runtime. Now the runtime, whether we're troubleshooting or not, can be manipulated. We can go 1-to-1, like every second you're working on it is the same as in the real world, one working second on it. But, let's say you fix a problem, or you suspect you fixed a problem, but how do you know? There's no air conditioning God that comes down and says, good job, son. You have to just kind of figure it out. It's working right. Probably don't want to sit around for an hour to see if it's cooling. So a lot of times you can speed it up to 60-to-1 ratio, and so you can see it cool, the space temperature come down, cut off, it'll cycle. That's probably a good indication it's doing what you want, okay? A lot of people forget that they left it on 60-to-1 and they can't see pressure switches that open and stuff because everything's happening so fast. So you speed it up, but you might want to remember to slow it down. Down here, depending on how complicated this is, you may have more than one circuit breaker, but on the air conditioners, we only have one circuit breaker. Click on. Now, y'all might can see on the projector, I've got the fan blade running for both the condenser and the fan. Can y'all see that from back there?
Yeah.
On the little screens, it's a lot easier. And so that's a dead giveaway. If you walked up a condenser and you heard it humming, but the blade's not running, you're probably going to go, I think it may be the fan. Or the capacitor, or the wiring to it. All right, and on the little computers, we can actually see bubbles flowing through this, little white lights, okay? So you can also see if the compressor's running. First thing I like to do, if it's running, is I'm going to put my gauges on there. So up here on the left corner, we have a bunch of tools. I'm pushing my gauges. So my gauges say 253 and 87, I believe, okay? Now, just like on 256 and 85. So just like in the real world, you can look at your gauges and read pressure. That's what it just did. But most of your gauges, you can look on there and there's a refrigerant scale that gives you a PT chart, right? At what temperature does it turn to a liquid? At what temperature does it turn back to a gas, right? Given that pressure. And so if you'll click on it, it'll show you that temperature. And so in other words, right now at 267, this refrigerant turns to a liquid at 122, right? Just like you would read on your gauge. Anywhere on the gauges there. The 79 pounds on the suction side is turning at 46 degrees. Okay? That's pretty easy. I'm just going to go through these tools real quick. All right? The next one is a temperature. We have two temperatures. Let me just, I'm going to take you can't tell it on this, but one is yellow and one is green, okay? And these are the different places you can do it. I've got it on the return air. I'm going to put supply air on the other one there. And so one is 83 and one is 68, okay? So we've got, and like I said, you can do it in a number of places. So we can get superheat, subcool, delta T here. All right, this next thing is a leak detector. And I wish the real world was like that. You see my leak detector there? All right. When I hit that leak detector, it is going to check for a leak for me. And in the little middle of it, there is a little green eye. So it's up for about 5 seconds. So if you're looking for a leak, it will flash red. It's not going to say leak. If it flashes red, we got a leak. So that's a lot easier than the real world. I've got an eyeglass. There are four or five places, depending on the program I'm in. I can check my outside condenser. Is it dirty or is it frozen? I can check my inside. I think I can check my filter on this one too. Okay? So we can visually inspect. Here they give me a performance chart. This is like you would find, of course you got a PT chart there, but you got a performance chart. These are pretty easy to read. These tell you, given the outside temperature and the inside temperature, what the suction pressure should be, what the discharge pressure should be, okay? So you could go, well, I don't know if it's high or low. Well, you come here and you can check it, right? It says right here, I don't know if y'all can read it from back there, my indoor entering dry bulb, 70 degrees. So I have a red line that runs up at 70. Well, down here on my stats, my indoor temperature is 81. So I'm a good bit above it, right? So I would expect to be above the red line, right? Let's see. What's my outdoor temperature? Ambient outside is 95, so I find where 95 and 70 cross. And if it was just 70, I would read it right across from about 260, but I'm higher than 70, right? So I'm going to anticipate a little bit above this red line read over, about 275, right? Same way, now with the indoor, do you see I have 3 lines? I don't know if y'all can see the 3 lines over here. So I've got a 70, an 80, and a 90, okay? And so they give us a little more chance to be accurate there, okay? So there's our performance chart. Let's see. My next one with the hammer and screwdriver, this is how you're going to troubleshoot. We'll go over that in a minute. A legend, some locking the contact, some of that stuff. So let's look now at my electrical. So they show us an electrical diagram here of my circuit here. You see this is a package unit, right? I only have one line voltage. this line voltage here, let's see, I have a crankcase heater, I have a compressor, a capacitor, a single contact on that, it's not a double pole. I have a indoor fan relay on my indoor fan motor. Let's see, outdoor fan motor, capacitor for both, a transformer signal, a simplified thermostat. I have an IFR. They like to use the solenoid symbol, not the coil symbol. But IFR is my indoor fan relay, CCB my contactor coil. Now, on this, I've got some added tools. First being a voltmeter, right? What did I say the rules with a voltmeter are? Across a source or across a load. That's all I'll do. So anyway, I got my voltmeter here, and here's the places you can check your voltage. Some of these mouses out here are kind of dirty, and so double clicking or getting it clicking just right seems to be kind of difficult. So sometimes you want to click on the tool, right, to bring that up. You should be able to double click wherever you want to go if you know, but those mice sometimes are no good. So anyway, a voltmeter. I have an amp meter here, right? So there's about 5 or 6 places I can take, 4 places I can take amps. Now I have an ohm meter here, y'all. Y'all hear that? What are my 2 rules of using an ohm meter? So I got to cut my power. Now, when I select ohm meter, let's say I'm going to go my compressor. R to common, 1 ohm. If you look, I know y'all are way back there, but there's a break right here. They have isolated one side of it, right? So there's quite a few places I'm going to click on my ohm meter to check ohms, just like you would in real world. Y'all, when I'm ready to go, I click my power back on. All right, what's my problem? I left my ohm meter on there, right? Okay, so that's how it's going to do it. Clear. Okay. All right, so there's my electricity. All right, so let me go back. And then see, I'm going back to the gears. So that's the regular picture. The lightning bolt is the electrical. So I'm going to exit this. Main menu, okay. Now I want to run a fault. I'm going to do some troubleshooting. Well, I'm going to come up here to faults. The second one says faults. You can do as many manual selections as you want, but they won't count toward the 10. Okay? If you want them to count, hit auto selection by user. It says quantity 1. Our program will only run 1 fault at a time. Hit OK. It takes a minute to load it up. It's going to work on that fault until you select a new one or you fix it. Okay? So I've selected a new fault. Now instead of run normal, I'm going to run the fault. Now this fault, I have a service order here. I got a package unit 3-ton AC. System is not adequately cooling and runs constantly. Okay. First thing I can do, what did I tell you? I put my gauges on. Right? I cut my system on. I see both fans are running. If I forgot what the problem was, there's a service ticket up here, okay? Somewhere. That's my legend. Service order. So you can get that back, okay? If you forget to write down. All right. Some of y'all's troubleshooting skills are better than others. Some of y'all's are not very good yet. So this thing is there to help you build off of symptoms. Matter of fact, as you get good, you go like, I wish I could just type in what's wrong with it instead of having to find the symptom. So it said it cooled inadequately, right, and runs constantly. So that's the only symbol we know right now. My pressure here, well, my temperature, pardon me, 232 and 79. That's kind of different from last time, isn't it? If I pulled up my performance chart, put it over here. If I pulled up my performance chart, 71 doesn't seem that bad, but 232 is definitely low. Let's see, 95-degree day. If it were 70 degrees inside, which it's 85, should be a minimum of 260, maybe 280. We're at 230. So there's another symptom. I got low head pressure. Okay? So let's go take a look at that. I go to the hammer, screwdriver, wrench, and here are my symptoms. Compressor won't run, all that kind of stuff. I know I got low head pressure. I can select that. But I'm going to see if I got something else. That goes, compressor runs constantly, inadequate cooling. So I'm going to select that one. Okay. Now it's giving me 1, 2, 3, 4, 5, 6, 7, 8, 9, about 9 or 10. Poor evaporator airflow, poor condenser airflow. Anyway, you can start at the top. When you do, let's say, poor condenser airflow. Now, I don't suspect this, but it's a possibility because it's just, remember, we're running off of, it doesn't do a good job, and it runs all the time. But I know that should probably be high head pressure. But anyway, I'm going to hit OK. The causes of that are 4 other possible causes, right? And so you could select any of them, and on some of them, once you select them, there's a test button. Because if you just do the repair, you're not really learning. Now, sometimes there's not a test. But you need to get good enough with this program to already know what the test is. Like, well, this is what I would do to fix it. So this is saying dirty condenser coil. What do y'all suspect dirty condenser? Before you go and clean it, what do you think the test for a dirty condenser coil may be? Test. Measure head and suction pressures and subcooling. This problem causes very high head pressure. Do we have high head pressure? No, we had low head pressure. So that's probably a good giveaway. Now we could have took subcooling, right? Because you've got a thermometer. Subcooling would be low. The coil condition can be inspected by looking at it, right? And so there is no point in me repairing that because it's not a dirty condenser coil. And if you do it, it's going to show up on what you did. In other words, I get to see a report where it says what you did. You might have changed every part on the piece of equipment. Okay? So it is. We be a little more efficient. Instead of just changing parts out, repairing everything. It's kind of like going out to a customer and going, I can fix it because I'm going to put a brand new one in. Okay? All right, y'all. So this is just like anything. This, you're going to get better and better the more you use it. Y'all got a lot of downtime when y'all are waiting for us to start class or in between classes. Please feel free to use them, and they really do help at this level. Okay, any questions?
It keeps up with everyone we do like I can do it there, maybe do 2 or 3 days. Yeah, you want us to tell.
I want you to, by the end of the semester, to have 10 completed auto selections.
Auto selection.
And now you can do manual selection, but you're going to select what's wrong with it then, and so it kind of takes the guesswork out of it. But I mean, they gave that so we can give tests. We can put something in. You can do far more than 10, but I'm gonna base it on you need to have 10 done by the end of the semester correctly, and but they've got to be tied to your name so I know how to give you the form.
So we working on one, basically working on a problem. You just can't find it because you just log off and come back maybe the next day and pick up at the same spot. You got to do it all day.
If let's say I didn't cover that, okay. Let's say I think I know what's wrong and I put it in there. I replace that part and I sit there and it seems like it's cool and okay now. Just like in the real world, there's nobody to tell you that it's done. So when you exit, if you didn't get it right, it doesn't say anything. If you got it right, it says, it pops up on the screen and it says, or it reads, problem has been.
Yeah.
It says something like this thing has been fixed. Now there's another message. Let's say you had something very simple like the condenser was dirty. You should have cleaned it, but instead you put in a new compressor, and so you fixed it.
Yeah, it'll say something
like you fixed it, but it might not have been the problem.
Yeah.
In other words, you spent a lot more money than what was needed.
So you got it may not have been a problem, so you really didn't get to the
Yeah, let's just say you had a leak.
Yeah.
If you had a leak, but you put a new compressor in, part of putting a new compressor in is pressure testing, vacuuming, and so that you would have fixed that leak. But that really wasn't what was wrong. All you need to do is fix the leak.
So you're not done until you get the correct.
That's right. And when you leave, it's going to stay on that fault until you insert another fault. You were saying, can I go back to it and work it? If you're on the same computer, yes. If you go next to it, that one's going to go back to the last one you run.
Okay.
All right, let's talk a little bit about some more lab work. Now, you got the computer labs to begin working on. I gave y'all a lab assignment to get good enough of those transformers where you felt very confident that they were good or bad, right? So some of you may not have your meters and you have to work on that. I also added some capacitors out there for the night class. So I would like you to test with your meter some of those capacitors until you feel confident with your meter that you're reading. Now over here, y'all see that plastic? I got a bunch of fuses. There's some other crap in there, but the fuses is what I'm worried about. Remember what it said about a good fuse here, right? What, 0.1? I would like you to test enough fuses until you feel confident that you can test fuses until the day you die. Okay? If that's one fuse, fine. If that's 30, do it until you feel good testing fuses.
How do we turn these assignments in? How do we let you know we have done it?
Because if you don't do it and you get out here when I start assigning these things, I'm going to see y'all are flat out missing what the problems are. Because trust me, when y'all open up the unit out here, it's a little more daunting than putting a fuse in front of you and putting it on because you know exactly what to do. You're going to put this all together. Do I have line voltage? Do I have control voltage? All right? But I'm not worried about a paper trail yet until we start on those units. Thank you. All right, y'all.
You said 3 things like what was those? Yeah, let me say cars. What the other 2 you said?
I'm sorry, what did I say again?
On the conductor, you said it was 3. I know you said copper, aluminum, and what else?
And contacts. In other words, most of ours are made out of copper, aluminum, or there's some kind of contact, brass, something like that, on a thermostat switch. done,